Hello, welcome to Short Circuits, and in this video I'm going to show you how to make a push-on push-off switch using 3 transistors. And that 3 transistor circuit also acts as a astable multivibrator, or you can call it a square wave oscillator. And to avoid that oscillation, I'm going to add one negative edge detector circuit which will convert that circuit into a T flip-flop. So let's get started. So first we need to make a latch. I'm going to explain you this circuit making process step by step. So here we have on the breadboard our basic circuit, which is transistor which acts as a switch. So we are going to slowly proceed with our making by simple logic. So this is the simple circuit. So in this circuit, this is a transistor and its emitter is connected to negative, its collector is connected to output. Output device is one LED, and in series with that is a resistor of 220 ohms. So this switch, let's call it S1. So when we press this switch, it will conduct and current IB will turn this transistor on and this LED will glow. As soon as we release the switch, there will be no current, transistor will turn off, LED will turn off. So let's power this circuit 3 volts and see if it works as expected. So yes, if we connect the switch to positive, the LED glows. Connect the base to positive and the LED glows. And if it is connected, the LED is turned off. So we want to make a circuit which will make this LED on even if we disconnect the switch. We want the LED to stay on. So that is our next challenge. And that is what a latch circuit is. So for that, what we need is, we need another transistor which is so this is a NPN transistor. It's NPN because it turns on when we give positive to the base, and this is a PNP transistor because it turns on when we give negative to the base. So this negative jumps here, and this resistor of 4.7K. Through this 4.7K IB flows. Let's call it IB2 because this is a base 2 and this is base 1. So this IB2 will turn on this transistor, the positive given to the emitter. So this is NPN, so negative needs to be given to the emitter. This is PNP transistor. It means positive needs to be given to the emitter. You can see with the arrow because positive flows like this. So this transistor turns on, this positive comes here, and this positive is fed to the base of this transistor again. So even if we release the switch, this transistor will keep this transistor on and the LED will continue to glow. But there is a drawback to this circuit because the gain of both this transistor are different. So we need to balance them both. So for that we need one resistor which will keep this both transistor in saturation. So resistor of 18K, this resistor goes to the positive because positive keeps it off, and this resistor from the base goes to ground because negative keeps it off. So these two transistors are hard turned off. With a trigger of positive, the LED turns on, both the transistors are on. And to delatch it, all we need to do is connect it to ground. Means if we press the switch, ground is connected to this base, this transistor turns off, which indirectly turns off this transistor, and the circuit is delatched and the LED remains off. So let's make this latch circuit on breadboard. So So now we need one BC557 transistor, which is a PNP. So in a PNP transistor, its emitter needs to be connected to positive, and the output is connected to base of transistor BC547. So this transistor controls the base of this transistor, and this transistor's output, which is our BC547, is connected to the base of our BC557, and these both resistors are of 4.7K. So now let's power on the circuit. I'm using 3 volts. So it's good to use DC source from a battery. You can even use 5 volts. So as you can see that the latch is not balanced, the circuit is not balanced. The output is on and it doesn't turns off even if we give a negative trigger pulse. It's not turning off. So what to do? We need to bias one of the transistor in such a way that it will move towards the cutoff region. What I am talking about is we need to just turn off a transistor a little bit. So we know this is a PNP transistor, so we have to give it a positive through this 18K resistor, or it can be any value resistor which is between 10K to 50K. I have given positive to this transistor's base, and now let's see if the circuit works. So I will give a negative trigger pulse and LED turns off, and now if I give a positive trigger pulse, the circuit is turned on. So negative trigger pulse will turn off and a positive trigger pulse will turn on this latch. So in this way this bistable latch works. So this is a simple bistable latch using 2 transistors. So the next thing we are going to do is we are going to make it a single switch on and off. So we have to make one circuit such that the output is delayed and it's given back to the input. That means first when we press the switch it will turn on, and then again when we press the switch it will turn off. So this is our main circuit diagram of a latch. This is for turning it on, this is for turning it off. So now let's design the circuit which will make it a push on push off switch. So this is the block representation of the latch circuit. So giving it a positive trigger pulse will turn this latch on, and giving it a negative trigger pulse will turn this latch off. Q1 is the output across BC547 and Q2 is the output across BC557. So Q2 is Q1 bar. That means when there is 0 here, there will be 1 here. 0 means ground and 1 is 3 volts. So 0 will turn on this LED when the latch is on, and there will be 1 across this Q2, and this internally keeps the other transistor also on. So this second transistor, which is our BC557, the output across it, we are using it to provide the input to our feedback circuit. So this will be our feedback circuit. So we are designing a circuit which will replace these 2 switches. So a single switch on and off. So how that is possible, I am going to explain you. So this latch, suppose this latch is on right now, the latch is on, there is 0 here and there is 1 here. So we know that the latch turns off when we give a 0 to the input, that means ground. So we need a circuit which will convert this 1 into 0, and that is a simple inverter, which is a NOT gate. So a NOT gate, this is a NOT gate which will convert 1 into 0. So this 1 will get converted into 0, and when we press the switch, this 0 will be fed to the input. The latch will turn off. So as soon as the latch turns off, Q1 becomes 1 and Q2 becomes 0, and that 0 is again fed to the inverter. This 0 gets converted into 1, and when we hit the switch, this 1 is fed to the input and the latch turns on again. So this switch is turning on the latch, and when we hit it again, it's turning off the latch. But there is one drawback to this circuit. So we are pressing this switch with our hands, and this switch is being held for some few milliseconds. Suppose it's 10 milliseconds, minimum is 10 milliseconds. So if the switch is held for 10 milliseconds, the inverter has a delay in few nanoseconds. So the whole circuit will oscillate at 1 gigahertz, somewhere near to 1 gigahertz for a few milliseconds, for 10 milliseconds. And when we will release the switch, it will settle to 1 or 0. Probability is 50-50. So there are 50-50 chances that the LED will turn on one press and it will turn off and on another press. But that's a major glitch, and to avoid that, we need to give a delay to this inverter, and that delay must be greater than 10 milliseconds, which is our holding time. So when we press the switch and release it, some people will hold it for 10 milliseconds if they are in a rush, so they will hold it, they will release it very quickly. But if they are relaxed, they will hold it probably for 100 milliseconds to 200 milliseconds, or even 500 milliseconds, which is half a second. So you must give this inverter a delay of maximum of 500 milliseconds in order to avoid the oscillations. So if this inverter is given a delay of 500 milliseconds, then it's safe. But if someone holds this switch for longer than 500 milliseconds, then this LED will flash at the rate of 1 hertz. That means for 500 milliseconds it will turn on, for 500 milliseconds it will turn off. So that is another application. So this circuit will act as a stable multivibrator if we short this switch and connect it directly to the input, or it will act as a push on push off switch if we connect a switch between this feedback circuit and this input. So let's design this delayed inverter. Let's see this circuit, and further we are going to merge this latch and delayed inverter, and this whole circuit comprises of only 3 transistors. So this is our feedback circuit, which is also a delayed inverter. So I have made it separately so that it becomes easier to understand. So if we try to make this block separately, then it becomes a delayed buffer, because I want to show you how this works. If you press the switch and it's pressed, so this transistor is on right now, and it will start discharging this capacitor. So as it discharges through this 47K resistor, which is a very high value resistor as compared to 4.7K. So it discharges very slowly, and when it discharges to a level when IB increases to a point when it turns the transistor on, the output voltage drops. So it takes time for this capacitor to charge to a level when the output voltage drops. So during that time the transistor remains off even if the input is low. So even if the input is 0, the transistor will output 1, and the 0 is delayed. That means a delayed buffer. It's just giving a propagation delay to the input data. If it's 0, then this 0 will be delayed here. So let's see the practical working of this circuit on the breadboard. This delayed buffer circuit is made on the breadboard, and as you can see, I have connected LED at the output. This LED will indicate logic 0. That means when the output voltage will drop, the LED will turn on. And this is the input switch. It either connects to 0 or 1. 0 means ground and 1 is 3 volts. So let's turn on the circuit and see how this delayed buffer works. So I will give input 0 and LED turns on after some time. You can see at the instant I give 0 to the input, 0 appears at the output after some delay. And this delay will determine the frequency of the circuit. And when we disconnect this switch, you can see that the LED slowly turns off. That means it retains the value of 0 and it slowly turns to 1. It gives delay to the input digital signal. So now let's combine this, our feedback circuit, with our latch circuit. So now we are going to draw our final circuit, which will act as a push-on push-off switch. So this is our 2 transistor latch circuit and this is our delayed buffer circuit. So if we look at this circuit, these 2 circuits closely, then we will know that this transistor and this transistor can be made common. That means this transistor can also act to turn this transistor on, and also it can discharge this capacitor. So all we need to do is make some changes in our latch circuit according to this circuit. So as you can see here, the emitter is connected to 4.7k resistor. So this emitter is to be connected to one 4.7k resistor, and then this whole circuit will be the same. One capacitor and one resistor, and now we don't need this LED, so we are going to replace this with one resistor of 1.5k. So this 1.5k resistor will be connected to 3 volts. This is our VCC line, and output of this transistor will be connected to the input of this latch. So this switch, when you will press the switch, it will turn on this latch, and when you press it again, it will turn off this latch. So I will redraw this circuit neatly and I will show you, and then I am going to make it on breadboard. So this is our final circuit diagram of the push-on push-off switch using 3 transistors. So this circuit comprises of 3 transistors. These 2 transistors make up the latch. So this block is the latch, and this transistor along with capacitor and resistor form the delayed inverter. So this is the delayed inverter block and this is the latch block. When we push the switch, normally there is 1 here. So when you push the switch, 1 goes to the base, this transistor turns on, the latch is on, LED remains on, and at the same time this transistor discharges this capacitor, and after a delay provided by this network, after some time interval, there will be this transistor turns on and there will be 0 here. So when there will be 0 here, when you hit the switch again, 0 will go to the base and this transistor will turn off, the latch will turn off. So in this way this circuit works. Now let's see how it works on the breadboard. So here I have made the circuit on the breadboard, and now I'm going to turn it on. I'm going to provide 3 volts. So this is the switch, and this is the base, and this is the output of our transistor feedback circuit. So right now it's connected to 1. So when we give a trigger pulse of 1, the latch must turn on. So it's turned on, and now the capacitor discharges, this turns on. Now there should be 0 here at the output. So this 0 will go to the base and the latch turns off. So this is a simple push on push off switch. And what happens when we held the switch? for longer than the delay, the LED oscillates between 0 and 1. So this is a flashing LED circuit. This circuit can also be used as a astable multivibrator to make flashing LEDs or generate a square wave pulse. If you want to avoid these oscillations, if it's causing problem in your circuit, then you can replace this switch with a negative edge trigger circuit. So this switch is replaced by a negative edge triggered switch. So when we give an input pulse, it will turn on only on the rising edge. So this switch will turn on for a short period of time depending on the rising edge, or it can be also made for the falling edge. So for that you must check out my video on the negative edge trigger circuit. So before replacing this switch with the edge triggered switch, I would like to show you one more fun application of this circuit. So all we need to do is connect one transistor to the output. So this transistor will turn off this transistor. So when we will hold the switch on, both the LEDs will flash alternately, and at the instant we release the switch, any one of the transistors remains on. The probability is 50-50 that this transistor will remain on. So this circuit becomes a simple heads or tails circuit. So at the instant we release the switch, and if you choose heads and this transistor is on at the instant when I release the switch, that means the guy who choose tails wins. In order to make this circuit working, we need to make the on time and the off time same. So to do that, we need to replace this 47K resistor with a 27K resistor, which makes the on time and off time same. But there is one more thing we need to do. We need to increase the frequency such that it's not detectable to the eye, and to do that we need to replace this 10 microfarad capacitor with a 2.2 microfarad capacitor. So let's see how this circuit works on the breadboard, and let's have some fun. So this is the heads or tails circuit made on the breadboard. Now let's power it on. So when we first power the circuit on, this transistor is off, the latch is off, but this transistor is on, which we connect to the output. So let's hold the switch on, and we have not replaced this capacitor with 2.2 microfarad because I want to show you the frequency. We have just replaced this 47K with 27K. Now let's hold the switch on, and the LEDs are flashing. So if I release the switch when this yellow LED is on, yellow stays on, and if I release the switch when red is on, so red stays on. But this should not be visible, this should occur at a very high frequency. So we'll replace this 10 microfarad with 2.2 microfarad like this. So now the flashing is very high. So now when we release the switch, we cannot tell which one will remain on. So what do you choose, red or yellow? I choose red. I won. I choose yellow. So yellow also remains on, probability is 50-50. So this circuit acts as coin flipping. This was the fun playful application of this circuit. Now let's replace this switch with edge triggered switch, which also requires one transistor. Let's convert this into a T flip-flop. So this is our final circuit diagram, and it has got many applications. So you can use it as a push on push off switch if you just build this much part. And to make it a heads or tails circuit, you just add this part to your circuit and you keep the switch on, the LED will flash. And if you want to convert this circuit into a T flip-flop, that means if you are using this circuit to make an asynchronous counter or in digital electronics application, so you need to make this circuit edge triggered, because there the toggling will create a problem. So you need to make this push on push off switch edge triggered, and all you need to do is make a switch which has fixed on time. So that can be achieved using a transistor and a positive edge triggered circuit. So when you press the switch, there is a rise in voltage, and this rising voltage is detected by this circuit, and there is one pulse. This pulse turns this transistor on for 1 millisecond, and this is how we get the fixed on time. So now if the on time is fixed, we don't need this delay to be large, it can be small. So we can replace this capacitor with a 0.1 microfarad capacitor. So let's see how this circuit works on the breadboard. So here is the circuit made on the breadboard, and now I'm going to power it on. So if I hit the switch once, it turns on. Hit the switch another time, it turns off. And if I keep the switch pressed, it doesn't oscillate because it's edge triggered. So this was the circuit. I hope you enjoyed this video and you learned something. So if this video was useful, please hit the like button, subscribe to my channel, and comment if you want to.